Well, welcome back, everyone. I hope you all had a great spring break. For me, it was a whole bunch of procrastination and fighting with the procrastination, but I got through the grading eventually. Any questions at all, folks, to start us out? Okay, well, we ended on a pretty nice spot actually last Thursday before the spring break. We closed out chapter three. Now we're walking into chapter four, applications of the derivative. And if you're looking at the Moodle website and seeing exam three there, you're realizing at week 11, we're still have a good chunk of stuff left to do, but we also have a good chunk of exams left. This is kind of a weird time to be in the class. Actually, in all honesty, spring break is tremendously disruptive. We all fall off of our normal school study routines and that kind of thing. And now we have to just pick it up right away, walking into this week. And the reason it's disruptive is further because this doesn't happen in the fall semester. You have Thanksgiving break, and then it's like 2 weeks left. But we've got a lot of stuff left to do. We're walking through these sections here. On this date, we'll have another review day ahead of the third exam. We'll have a normal day for doing content on this day here. This entire week is going to be closed week, and so we'll just be reviewing for that week there. So it looks like 1, 2, 3.5 instructional weeks, an exam day, a full review week, and then a final exam day. Friday, May 9th at 10 a.m. That's a pretty early hour, but we'll make it work some way, somehow. And the reason this is, again, kind of rough having a spring break right here is not just the amount of time left. There's a significant amount of work to do, about a month's worth. It's also because there's also, let's see, 35% of the class left over just in exams. That's a big chunk. So that means everything you do at this point of the class now, towards the end, getting into finals week, is the most pivotal part of the class. It's rough that spring break happens, it kind of disrupts us, but we'll get through these last weeks, pushing through. They'll be like the light at the end of the tunnel once we're on this week here reviewing. And well, that's my spiel for be careful coming back from spring break. It's hard actually getting back into an ordinary school routine after it, especially with so much still on the table with the exams. Aside from that, we're going to work through really just as much content as we can, do a natural, normal review before going into that third exam week, and then pretty much just review. That's our plan so far. Any questions or comments at the moment, folks, before we get started? Yeah. Doesn't look like we're going to make it through the content listed on the syllabus. If we try to get through that, we'd have to just sort of race through the material at that point. We're going to continue to go at our steady rate with the hope of getting into some integration problems to well round the course. We're not going to make it into chapter 6 with as many applications of the integral, unfortunately, though. Other questions so far? Okay, well, for now, applications of the derivative. In chapter 4, that's where we are. We're looking into maximum and minimum values. Then the next section, we're going to apply that to find maximums and minimums of functions. Then finally, we get to our big application section. I mean, this is an application chapter of finding maximum and minimums in actual applied settings. So that's going to be the major structure of chapter 4. The last section is on dealing with something called antiderivatives, taking the process of finding a derivative and reversing the entire process. That's our link to get into integration in chapter 5. So it's a little bit weird in chapter 4, but we'll get through it. Starting with maximum and minimum values. I mean, that's a great start, and that's what chapter 4 is all about. We're looking into optimization when we are talking about applications. So by optimization, we were wondering, when does a process minimize? When does it take the least amount of time? When is it maximized? Those kinds of issues. And so we're just turning the discussion now over to maximum minimum values. This is sort of the easier definition for absolute maximum, absolute minimum. And then suddenly it gets really tricky when we talk about local maximums and local minimums. So some of our major work in this section here is just to spot the difference between these two concepts already. So when we say an absolute maximum, we need a value of f. When we say a value of f, we're talking about an output. So it's going to be a y coordinate. So it's going to be some value that exceeds f of x for all other x's in the domain. That's what we'll mean by an absolute maximum. And a minimum value is just going to be some value of the function f, so that f of c is always less than or equal to f of x for all other x's in the domain. So if we find a value c that makes this estimate occur, that's our minimum. If f of c exceeds f of x for all other values, then that would be our maximum. Other words are global maximum or minimum as opposed to absolute maximum minimum. Or instead of saying absolute maximum, absolute minimum, you could refer to them both by just saying the extreme values of the function. I think these words are used a little bit less in the textbook, so I'm mainly just going to say absolute max, absolute min. And we'll practice this right away. Here's a problem right down below. State the absolute maximum and absolute minimum values of the function. Let's give this a try. I'll match up the color coding, blue for max, green for minimum. And on this one, probably the big giveaway already is there's a minimum for sure, right? This is the function y equals x squared. And the lowest value this function takes, recall we're talking about the value of f, which is referring to a y-axis value, is right here on 0. So we can say the absolute, I'll abbreviate to ABS, min, I'll abbreviate to min, is going to be 0. Does that make sense to folks so far? Okay, so for the value of f, again, we're thinking of the y coordinate values, and on the y-axis, the smallest coordinate ever picked up is 0 itself. But notice I skipped the absolute maximum to find the absolute minimum first. Let's write that in. Absolute max. So it has to be a value on the y coordinate. It has to be an actual number, so we can't say infinity or negative infinity. Any volunteers for what answer we should supply right here? Kind of an uncomfortable problem, right? What's sort of not helpful is that there's no values whatsoever on the y-axis. There's just a little mention that the domain is from negative infinity to positive infinity. But what that then means is if we're on this curve, we can go up forever. There's no stopping, because if the domain is all real numbers, then just put in a larger value of x, say larger than 2, and we just go up. Put in a value 3, and we're just getting higher and higher. This is, sorry, say again? Good call, absolutely. There is no absolute maximum. You can say does not exist, simply none, undefined, anything like that would do the job. Let's go with that common acronym you mentioned, does not exist. It's rude to not define these when you use them, so let's define it once on these notes. As a reminder, does not exist. So already it's kind of a tricky problem, right? To spot maximums and minimums, reading them off a graph. But that's what example 1 is really meant to be. It's 4 tricky questions where if we can spot the difference between max min on all 4 of these scenarios, we get a really good understanding of how this all works. So let's try it out again. Just put a little quick border here. This problem is not as bad, right? And that's because the domain has been tied off to a closed set going from 0 to 2. That means we end right here on that solid dot, and we end down here on the solid dot. There's like a light part of the graph, like a shadow. It's just the remainder when we deleted the domain from the original function. So this time we can say for absolute maximum, the absolute maximum is not 2. That's already kind of shocking in a certain sense. Recall when we say the absolute maximum or the absolute minimum, we are always talking about the y coordinates, the y values, the output to the function, not the input. The input is 2. We get the absolute maximum by taking that 2, feeding it to the function, which means we land here. We grab an output somewhere on the y-axis. Here's how the function's computed. You square whatever the input is, outputting a 4. That gives us an absolute maximum of 4 itself on this one. But it's really super tricky, actually. When you do these on the homework problem, incredibly tempting to give this a value of 2, and then we miss the question. I mean, you're right, the maximum occurs at 2. We want the maximum value itself, the 4 in there. And the absolute minimum, the same. It's just going to be 0. We'll say absolute minimum, 0. So that's 2 graphs down. What made this graph actually have a maximum and a minimum all at the same time is the fact that the domain was closed off. When we go to the full domain, there could be a maximum or a minimum, but in this particular function, there was only the absolute minimum, no max. And then it gets weirder still, but any questions so far? Okay, here's where we start to lose stuff even more on the domain. Notice what we've lost. Every time we go to the right, we're losing something. Here we're on a closed set from 0 to 2, which means both the boundary values of the domain are part of the function. That's why there's a solid dot here and a solid dot up here. But on this one, we lost the lower bound. 0 is not included in that set whatsoever. And that's why there's an open circle in that location. Like before, there is an absolute maximum. It's at that height by the red dot. So we can start by saying absolute max 4 once again. Here's where it gets tricky. What would you all say for the absolute minimum on this one? It can't be 0 because we can't even put 0 inside the function. It's out of domain. So 0 is off the table, making this question way more weird than this one when we put in a does not exist. I mean, I'm not saying the answer isn't the same, but what would you all say for the response on this one?
Greater than 0? Or did you just say does not exist?
Greater than 0 would force us to say which number greater than 0. We would have to tie it down, right? The moment we try to tie it down, we get in even bigger trouble. Here's what might happen. Let's imagine we blew up this number line, just the horizontal axis. Here's 2. Here's 0. So right where the red dot was, I'm visualizing it as that open circle right at 0. We can't put 0 in the minimum. We can't even put, say, 0.1. That's not the minimum either, right? Because there's like this infinite game that will never end. If you tell me the minimum is 0.1, I just simply have to divide it in 2. I find something smaller, 0.05. That's not the minimum either, because I can divide that by 2 again, find something smaller, 0.025, and this game has no end whatsoever. You can keep dividing by 2, keep finding a domain value inside this function, keep getting a lower value on the y-axis, and it's unending. Because this is an unending process, this is a really weird one. There is no minimum, so we could say does not exist. We could say none or undefined. It's just a weird issue of, this is topology now, if you're curious. You take a closed set and you lose the boundary value, you have also lost the minimum to that function at the same time. It's just a weird thought on how that works. Does the analogy up here help out, seeing how there's always a slightly smaller value to anything you pick? Okay, to me, I think that's a clean way to see it, but everyone sees it slightly different visually. You could think of this differently as blow this up a whole bunch. You can get closer and closer to 0, as close as you'd like. Say you're right here, but each time you get even closer to 0, you take a value that keeps on changing, dropping lower and lower, and there is no limit to how low it drops, except for 0 is the limit. Yet you can't put 0 inside the function, it's out of domain, and that's the only reason there is does not exist on this one. So there's something really weird going on with the closed set. Calculus loves closed sets. The moment you blow one of them open like that, so this is half open, half closed, we've got a problem. And if you've lost both boundary values, now it's a full-on open set. we have major problems on this one. So that's really the big difference on what's going on with this. If you're curious about these kind of weird little issues, again, this is a subject of topology. In topology, we'd call this a closed set. And what we saw here is that a function on a closed set has an absolute maximum and absolute minimum. It turns out this is not a coincidence. Every function continuous on a closed set will have its maximum and minimum. So this turns into a huge observation. But over here, this one is an open set. Open sets are the ones that behave not nicely. They have this weird pathological behavior, like we saw in the minimum does not exist. On this, nothing exists. There is no absolute maximum because we lost the boundary value at 2. There is no absolute minimum. So we'll say absolute max does not exist on this one. And also the absolute minimum does not exist as well, making it a pretty tricky problem. Well, any questions at all, folks, with the discussion on maxes and minimums? Okay, well, this was our problem getting started thinking about the topic. And now we have another weird topic to take a look into. Before we just jump into the notes, let's plot something to get a feel for this. So let's put in a polynomial that goes maybe y equals x cubed plus 3x squared. And that looks like a pretty good polynomial already. On this polynomial, this value right at 4 is not an absolute maximum, right? It's because if you go way over here, this value exceeds it. Second coordinate is 6.3. On the solid dot, the second coordinate is 4. However, it's like a maximum, right? If you restrict your attention to this, we have a maximum right here. We'll call it a local maximum. It's not a global one. It's not an absolute maximum because if we look at the whole function, things exceed it. Likewise, we'll call this one a local minimum right here, right at 0, because locally, it's the smallest point on the function, just like on that graph down below. It's not an absolute minimum because if we zoom out, this value, let me highlight that again, this value out here is way lower. So this curve has no absolute maximum, no absolute minimum whatsoever, but it has special points, local max and a local minimum. So that's the next idea we want to get into. So here's how the definitions work formally. We say f of c is a local maximum. Pull up that graph as we read that. If, let me zoom back in on that region there. We have a local maximum. If f at c, that would be 4 on this problem, it's greater than or equal to f of x, when x, that's the -2 part, is near c. So for near that c, which is -2, second coordinate is always below 3.69 here, 3.99 here. That's the maximum right at the value. So that's what we mean by a local maximum. The local minimum would just be looking at this region, like we said before. Local minimum says if we're near c, the value 0, then f of c, that's the other coordinate 0 right here, is always smaller than every other value f of x. You just have to be nearby c. What do we mean by nearby? That's also kind of an open question right here. When something is true near c, we mean it's true on some open interval containing c. So in this problem down below that we're looking at on the screenshot, the open interval might be, say, from here to here. If your x is in this open interval, then for every x value inside this interval, they're always going to be larger than 0, except for that one value where it's exactly 0. So if you can make it look like a minimum on small little open interval around the value in question, that's what makes it a local minimum or local max. Well, This is very tricky, like we mentioned, so here's the cautionary tale about this coming up next. When it comes to local maximums, you have to put an open interval near C to show that it's always lower or greater than through those estimates. But that gives us a problem if we're dealing with an endpoint of the domain. If we're right at the endpoint of the domain, you cannot fit an open interval around it. Say, for example, on that endpoint right there. Let me extend out the x-axis. I can't put an open interval around 1, 2, 3, 4, 5, 6, 7. Sorry, I had to count those out. There's no open interval around 7 because the interval might look like this if we try to force it. That is an open interval, but to the right of 7, there are no function values whatsoever. So that's what's breaking about this discussion about local maxes and local minimums. And that's why we have this statement. There's never a local max nor a local min at the endpoints of the domain of a function. That's because we can't fit an open interval if we're right at the endpoint. There's no movement or room to the right to move or room to the left to move. So this is a big cautionary thing to watch out for. And it gets confusing because we're only talking about local maxes, local minimums. Only the local maxes and minimums have the boundary value problems. But if we're talking about absolute maximum minimums, doesn't matter if we're at the boundary value or not, they will exist. In fact, that happened up here. This one had a boundary at 0, a boundary at 2 on the domain of the function. Both the absolute maximum and the absolute minimum existed. So with those ideas together, on this problem, example 2, we're going for all local maximums, all local minimums, as well as all absolute maximums, all absolute minimums, everything that we can find. Essentially, we're looking for any extreme value whatsoever. Any questions at all, folks, before we give it a try? Okay, let me just decide on where to zoom into. Let me take this part right here. Let's scroll down just for the sake of space. I will answer the question by looking at just that component of the definition. So that'll zero us in a little bit better. If you're given a graph like this is a pretty common exam question on exam 3 or the final exam. A good idea is just be really, really methodical. I'm going to work left to right and try to spot everything possible. First, might be a good idea to just put some numbers here, so we're not counting these off each and every time. That's kind of annoying. Okay, now with our scale fixed a little bit better, we'll go left to right. On the left, it's already a trick question. Let me do one small change, which we're going to correct immediately, so we don't have to copy this down. If it looked like that point filled in, we would have said 5 is an absolute maximum to the function. But it's open. That means there's no extreme value whatsoever right here. It's not a local maximum because we're at the boundary value of the function. Local maxes and mins can't occur. And it's not an absolute maximum either because it's missing in the domain. 5 never actually occurs as an output to that function. So we might start by saying x equals 0, none. This is a way to say we handled that point. Now we're moving on to the next interesting piece. At x equals 1, nothing interesting is happening, so we can move on to x equals 2. At x equals 2, something is indeed happening. And it is, again, really, really tricky to see just exactly what's going on. Well, there's either a local maximum or a local minimum right at 2. How do we find it? What we need to do is place an open interval around 2 and just see what happens with the function values. If x is near 2, do we have a maximum or do we have a minimum? So we restrict our attention to something like this on the y-axis. Let's add kind of like a guideline temporarily. You might use note cards or your hand, maybe your calculator in an exam room to really do this, or you could use something a little bit more heavy-handed. Just delete the part of the function you're not interested in looking at, cover it up somehow, pretend your whole entire world for this function is right here. This is all that matters. Locally, right around 2, is that 1 point a max or a min? Anyone spot the difference? Good call. We are looking at a minimum because the height at 2 is below all of the other outputs. These are right around 3. These are going from 3 to 4. That one's the minimum. So let's bring in the whole function. It's pretty distracting seeing everything at once, but we can say at x equals 2, we have a local minimum. The local minimum value happens to be 2, but think of that as the second coordinate we're always outputting for that minimum. So 1 down, it's not an absolute minimum because there's other values even lower than that one, but it was certainly a local minimum. Kind of tricky in a way, but does that make sense to folks so far? Okay, let's keep on proceeding through. Once we handle 2, again, be extremely methodical with this. It's so easy to miss information. Just move on to the next one. No, when we were at 1, I said nothing interesting happening. That's because the function is just decreasing right at 1. There's no maximums nor minimums whatsoever. That was interesting. That was a removable discontinuity. And at 3, that's also interesting. That's a horizontal asymptote. And anytime you see a horizontal asymptote, that's probably leading you to a local maximum, local minimum, but not always. We have to be very careful. But that is interesting right around 3. If we're at 3, we put in a small open interval, say from 2.5 to 3.5, so that this is the part of the function that matters. Between the orange bars, we get a point way out here at height 4. We would call that a local maximum because right around in this range, 4 is the highest function value. So let's write x4 results in local max. And the local maximum value is not 3. We always give the second coordinate. The height is at 4. Oh, yeah, that was x equals 3. Thanks for spotting that. This is at x equals 3 itself. The part that was highlighting, that should have helped me out, gives us a maximum of 4. Any questions so far, folks, with those? Okay, we're nearly through it. So on the next one, we were at, oh, I deleted a lot, 2, 3. We were at 3, so moving now next to 4. That's a really interesting point. We have a lot to say about what happens at 4. Right around 4, 2 things happen. Notice that we can still say that there is a local minimum, right, relative to 4. Because if we restrict the domain of this function, then that's the lowest function value. But some people might have felt that's a weird thing to say because, it's not just a local minimum. That is the lowest point on the entire graph of this function. It's an absolute minimum at the same exact time. And nothing in our definitions prevent one function value resulting in 2 kinds of minimums. So on this one, we can say, right, at x equals 4, we have an absolute min, and the absolute minimum is at height 1. And it's also a local minimum at the same exact height 1. So this one's a kind of interesting one, whereas at x equals 3, we had the horizontal tangent line, which meant here, f prime of x was 0, but that's different. You can't put a tangent line on a sharp point like that. This is where f prime of x does not exist outright. That's a sharp corner right on the graph, and that's where differentiability actually fails. But notice what that's telling us so far. Derivative didn't exist at x equals 2 either. At x equals 2, f prime x does not exist because we lose continuity. The derivative is a continuous function, So if we were differentiable here, we would have had continuity. Essentially what this is telling us is, it looks like if we're looking for maximums and minimums, we should be looking where the derivative doesn't exist or where the derivative is zero outright. That's the pattern we see already with all this work. So that's just a side observation. Let's now move on to the next interesting value. We were at 3 and 4. Now at 5, the function is just increasing. We're going to totally skip that. There can't be maximums or minimums if you're just increasing outright. But at 6, that is interesting right out here. That's not an absolute maximum because function values out here are higher and even way out here are higher. But we can say locally nearby 6, say around 6.5 to 5.5, this point is the highest point altogether. So we have a local maximum. Let's write x at 6 yields a local maximum value out here at height 3. So it takes care of the function value right at 6. And then it gets really confusing at 7. When we're at 7, well, it cannot be a local max or a local min. We're at the edge of the boundary. That's where there is no local maximums and minimums. It's also not an absolute maximum nor an absolute minimum. To the left, there's higher function values and lower function values. So this boundary value point is also extra confusing. Let's write down at x equals 7, none. Deserves an exclamation mark right here. And let's put in one extra clarification because it's a tricky enough process. None because local min max values cannot occur at the boundary of the domain. There's an exclamation mark because, again, really subtle, slightly tricky ideas in these kinds of problems. But we did it, folks. This is the process of running through a graph, determining local minimums, absolute minimums, and same for the maximums. Really kind of a tricky problem. Watch out for things like the open circles. Those are always extra confusing. But really, honestly, the bigger takeaway from this is we're looking for maximums and minimums when we don't have access to a graph. And going through this problem already gave us some hints. If we want to find maximums and minimums, find where the derivative is 0. That's extra special. And also analyze where the derivative fails to exist, because that could be where maximums and minimums occur. It's no guarantee, it's just a place to start looking. Well, let's take a look into the next concepts. What we want to take a look into next is some related theorems are going to help us out. We're going to look into the extreme value theorem, Fermat's theorem. We'll eventually talk about a critical number, but notice the tie-in. A critical number to a function sounds super important, right? It's where there's a horizontal tangent line. The derivative is 0, yields that horizontal tangent line, or the derivative does not exist. Based on the problem we just looked at, those critical numbers are the first place we start to look for maximums and minimums. Then we'll just tie this all together into a process called the extreme value theorem. This theorem says, if you have a function that's continuous on a closed interval, recall that was a really special ingredient for us. Continuity on a closed interval gives us a lot. In fact, gives us a guarantee. You will find an absolute maximum and you will find an absolute minimum to that function outright. And this is just a method of doing that each and every time, even when there's no graph available for us. So we're going to lead on towards a method, but to get there, we need to first take a look into the extreme value theorem. This sounds important as well, but what we mean by the extreme value theorem is this is a theorem that guarantees an absolute maximum and an absolute minimum all at once. All you need is continuity, and you also need a closed interval. So if your function has those two properties, it must obtain an absolute maximum. There's no other way to do this. It must obtain an absolute minimum. You're essentially cornered into those conclusions. Well, that's good. Being able to find an absolute maximum and minimum and guarantee they exist is a great situation to be in. But this theorem is also quite a bit about its hypotheses. So let's take a look at it from this point of view. What could go wrong? In other words, in case one, the first column, we're going to say F not continuous. In case two, so second column over here, we're going to look into the situation interval is not closed. That's hugely problematic as well. And on the right-hand column, we meet both of the hypotheses of the extreme value theorem. F is continuous on a closed interval. So these are the three interesting situations that can occur here. Let me just change my formatting slightly. So first one, F is not continuous, but we have a closed set. Sorry, question first?
Yeah. Like a straight line all the way across.
Yeah.
If that means it would be continuous and it would have those intervals, but what would be the? I'm just curious.
That's a great question. So let's do that on this graph right here. I'm going to do all my graphs pretty much in quadrant one, so we just focus on the graph itself. We said we had to be continuous. It had to be a closed interval. Let's say the interval goes from A to B, and we want linear, like you said. Let me start right here. The fact the interval is closed means we're starting on a closed dot. That's an actual function value. At B, we'll go over here. Then, if that's our function, we'll say that this output right here leads to the absolute min. Let's just call it f of a. F of a is absolute minimum on this one. And we can say for this output here, this is going to be f of b. F of b is the absolute maximum now. So if it goes linear, pretty much now just your endpoints are giving you the max or the min in that case.
It's not a straight horizontal.
Oh, I gotcha. That one is even cooler. If it's a straight horizontal line going like this one, it's extra tricky. So let's analyze it through the lens of the official definition so we can get a good view on this one, because that is a tricky case. It feels like it breaks everything, except the person who wrote this definition baked in a small fix for this particular reality. So if we go from A to B horizontally like this, here we go. That means the function value that goes here is both f of a, which is equal to f of b, all at the same time. And this seems kind of silly, but what it would then mean is that f of a, which equals f of b, is the absolute max and min all at the same exact time. Kind of weird, but let's think about this. What's going on with f of a? Well, f of a is at this height. If it's an absolute maximum, then for every other function value, we should have greater than or equal to. It's because of the or equals to. Everything is equal to height f of a. Every point on this line is simultaneously absolute maximum and absolute minimum all at once, including the boundary values this time. So it's because they baked in that greater than or equals to, less than or equals to. We just have strictly on this problem equals to straight across the board, and that's allowed in our definition. So that's a really interesting case. It's kind of a weird one, but it absolutely fits into this kind of process. Other questions at the moment? Okay, let's leave this one in as kind of the weirdest case ever. We looked at another one that you can access through the video if you rewind a bit. But now let's look at the bad ones, where we lose something from the extreme value theorem. continuity and the closed interval is essential to guarantee you really have an absolute maximum and absolute minimum. To see why, just delete one or the other. Let's delete continuity on this case right here. We're going to still have a closed set. So it's going to go from A, put a solid dot somewhere, B, put a solid dot somewhere else. It can be above or way below, totally your call. But I've lost continuity on here. Anything can happen. It could do something like this, for example. L, if it does that, A is the absolute minimum, B is the absolute maximum, but it was continuous. That's not even allowed, right? So you could have done this. We lose continuity if we put in a removable one, and we still have an absolute minimum and an absolute maximum. So this is an okay case because the discontinuity wasn't too major. I just deleted 1 point from the curve. But there are other discontinuities. This theorem is not saying if you lose continuity, you'll never have an absolute maximum or minimum. What it is saying is if you have both, you're guaranteed the absolute maximum minimum. So if I lose continuity, we could have an absolute max or min, but if I draw the function just right, make the discontinuity severe enough, we could lose it. Here's what I would consider a severe discontinuity. An infinite discontinuity by introducing a vertical asymptote. Let this point do this. Let this point do this. And now we've got a major problem. The interval has a point here at A, so it's closed on the left, it's closed on the right, and you could define a singular point right here to make it be the entire interval from A to B. So the fact that there's a missing point in the middle isn't even the problem. You could introduce one, leave it blank like this to just convey there is 1 point gone, but now there is no max because the curve goes up forever, and there is no minimum because the curve also goes down forever. Any number you supply as a maximum or a minimum, I could find a higher value than your max and a lower value than your minimum. Just a bizarre function, and it's because we removed continuity. This one's allowed. No guarantee of maximums or minimums for this kind of function. And again, even losing the closed interval is just as bad. But any questions on this case one here? Okay, now next for case two, we'll say f is continuous, but we lost the fact that we have a closed interval. Because it's now continuous, I can't put in something like this in the middle of the interval. That would lose continuity. But you're allowed to do something like this, however. Go from A to B, and I forget, the interval is not closed, so I can't even start on the solid dot. I'm gonna start on an open dot, and let's see here, maybe, and on an open dot as well. The curve could do something like this. I'll draw in a new one in just a moment. If the curve does that, there is an absolute minimum. It's right down there by the red dot. We might have had an absolute maximum, but if the curve does this, it's a simpler curve. This is almost not even fair, right? The more complicated curve had an absolute minimum, but this one, the straight line linear, always going up, not this linear version over here. This one has no maximum, no minimum. It's kind of like the second or third question we were looking at the top of these notes. So no max, nor min value. So strangely enough, if you put these together, continuity, closed interval, those are the minimum two conditions that you put on a function f in order to guarantee the absolute maximum and the absolute minimum. Now, no matter how hard you try on this, if you try to make this go up forever, because you're continuous, it has to come down. And this one would have an absolute max up here, absolute minimum down there. Nothing you do on this is going to allow us to escape that reality. Let me go back to the tricky example, horizontal. So this is what the extreme value theorem is all about. Conditions on which you are guaranteed an absolute maximum and an absolute minimum. But what the theorem doesn't tell you is how to find them. That's kind of rude. That's what the closed interval method is all about. It tells you the method to finding them. Extreme value theorem just tells you they're out there. Well, next thing we want to take a look into is going to be Fermat's theorem. But first, a last question, folks, about the extreme value theorem up here. Okay, Fermat is an interesting mathematician. I believe he's French from around the 1700s. He has one theorem named Fermat's last theorem that caused a humongous amount of drama in the mathematical community. If you get bored and want to Google that on YouTube. But what this is about is slightly different. We're going back to the thought of when is there a maximum and minimum? We want to look at when f has a local maximum or minimum at C, and if the derivative of f exists, we'll get this conclusion. The derivative of f at C has to be 0. That's the whole content of Fermat's theorem. So it tells us this is a place to look where the derivative equals 0, or later on we'll say also when the derivative doesn't exist, to start finding maximums and minimum values. For a related function like we were discussing, this one here, it says if f has a local maximum or minimum, that's a local minimum right there on the solid dot. Does the derivative of f at 0 exist? Yes, it would be 0 itself. That's what that conclusion is saying right away. Then the derivative of f at C would be 0. There's a huge danger with Fermat's theorem, however. If we're looking for maximum and minimum values, we'll very often take the derivative like this is indicating, set it equal to 0, and solve for values. But those values don't actually guarantee you're going to be finding a maximum or minimum. This is what's going on with this function f of x right here. Let's examine it really quick here to see what's going on. It's a power function. It's not a complicated one. If you take the derivative like this is indicating, then f prime of x, come back over here, is going to be 5/3. X to the power of 1 less, so there'll be 2/3 up here. Now if we do this, set f prime of x equal to 0, that will then imply, take this whole fraction, 5/3, x to the power 2/3 is now set equal to 0. And that's not a bad equation to solve, even with the weird exponent 2/3. You could clean it up if you like by multiplying both sides by 3/5. That'd just be feeding 3/5 to 0. You just get x to the power 2/3 equals 0. And as far as real numbers go, only one solution to that. This would mean x is 0. However, we can't put that value for C inside and say f has a local maximum or minimum at C. Sure, the derivative was 0 right at that location, much like derivative is 0 down here. This one did lead to a local minimum, but we have a weird issue on this one. Even though f prime at 0 is 0, that 0 right there is a 0 we solved when we set f prime of x equal to 0. It's the number C that's being referred to right here in Fermat's theorem. Even though the derivative of f at 0 does come out as a 0, y equals f of x. Now we're talking about the original function, has no max nor min of any kind, absolute or local. Let's take a look at the function just to get an explanation of why that is. The function is x to the power 5/3. It plots this way. And right here at 0, there's in fact a horizontal tangent line. If you draw a line that goes through like that, that's the tangent line there. But it has kind of a weird feature, right? Right at that horizontal tangent line, it's increasing, pauses, but then continues to increase. That means there's no maximum whatsoever right at 0. There's no maximum at all. This just keeps increasing to the right, keeps decreasing to the left. So this is the view of the function we're actually dealing with on this one. No maximum nor minimums whatsoever. Doesn't mean Fermat's theorem is useless to us. It's still a big help. Because like we mentioned all along, finding where the derivative equals zero, or finding where the derivative just doesn't exist, that's the first place to look. But what this problem is about is, it's not a guarantee. We have to do extra analysis after we find those values that makes the derivative zero, like down here. This is a problem we'll come back to because this is kind of an explanation of why our methods are so hard in the follow-up sections when we actually go to do optimization. We have to take extra steps to avoid this kind of outcome. But we still start at doing this, setting the derivative equal to zero and solving. That concept is so important that it has a name. What we're doing is finding the critical number to the function. And in chapter 4, a lot of our methods are pretty much this. If you get stuck on an exam and you just differentiate, set it to zero and solve, you're probably getting a lot of partial credit because this is a core technique. The critical number to a function f is a number c in domain of that function f, such that the derivative is zero or the derivative just does not exist at all. So let's practice finding those critical numbers. Then in our closed interval method technique, down below in the notes that we took a look at, that's the first step, find your critical numbers. So let's give this a try. You have to be concerned about the domain of the function, so let's do a bit of a domain analysis as well to help us out. Your critical number has to be in domain. Well, on our first problem, we're dealing with a polynomial. That means the domain is R, all real numbers. An interval notation, that's negative infinity to positive infinity. So we have no real issues of the domain being smaller than we think it might be. But on this one, we do have issues when we do part B. Domain of this one is, think of what the problem could be. If there's a denominator, your problem, it could be division by zero, and that could only happen if x is negative 7. That's the one value we have to throw out. So domain is negative infinity to negative 7 union negative 7 to positive infinity. Putting it in orange just to convey, you don't have to write this down on paper, but it's good for the notes because it captures this concept of the definition. Now, we'll go through part A and part B. First thing we do is that part. It says f prime at c because it's referring to c over here. But really what we do is we just calculate good old f prime of x. Nothing too different from chapter 3. Because it's a polynomial, this is a really rapid computation. It's 3x squared minus 6. Then we want to simplify that as much as possible. Nothing too much to do on that. Next step is immediately set it equal to 0 and start solving. We did it. We set equal to 0 right here in line, and now we begin solving. Let me just convey my highlighting a little bit better. Well, that should be fine. So to solve this equation here, ordinarily we might factor this, but if x appears in just one spot, the better technique is just isolate x squared. So we'll get 3x squared is positive 6, divide by 3, x squared is positive 2. Be careful on this step. When you take a square root, you get that x is equal to positive or negative square root of 2. We don't have to worry about the domain. Those are automatically domain values. We can just say right at this step, these are the critical numbers of f. So if this has maximums and minimums, what this is telling us is those are the first places you would want to take a look into it. Any questions at all, folks, on that method with critical numbers? Okay, as far as example 3 goes, really the only thing we're doing new, in addition to what we did in chapter 3, is just this part in the yellow where we set the derivative to 0 and start solving. Why would we do that? Just always keep in mind that f prime of x always is equal to the slope of the tangent line. We insisted when we set that derivative to 0 that the slope of the tangent line be horizontal. And now we're saying at those values, those inputs, it will result to outputs for horizontal tangent lines. Let's see if that really tracks. Let's put in the whole function. X cubed minus 6x plus 2 here's what the function looks like. And square root of 2, just for a quick estimate, is positive 1.41. Here's negative 1.41, and we have a local maximum. Here's positive 1.41, and we have a local minimum. It actually worked out as intended. Those two critical numbers directly took us to a local maximum and a local minimum. So that's the idea of what Fermat's theorem was trying to communicate, as well as what this technique is saying right here. But it doesn't always work out. That's why there's so many extra steps. Always keep this graph in mind. Just because you found a value that set the derivative equal to 0 does not mean you really found a local max or a minimum. Just depends on the geometry of the function itself. So it's an interesting technique. It's finicky, but we'll try it again in part B just to see how it goes for this one. Let's include a screenshot just to get some of this information kind of connected. The critical numbers, the local minimums and maximums. Okay. Any questions at all, folks, before we try a second version? Okay, here's our second version next. A little bit more built up this time, only because now we have to use the quotient rule. But this one's not too bad for as far as quotient rule would go on it. Nothing too built up in the numerator nor the denominator. So we'll start by saying, take f prime of x. When we do the quotient rule, if you feel like you've done this a lot and you're getting really great practice, you might have just went, the derivative of the numerator is 1, times the derivative of times the denominator copied, numerator copied, times the derivative of the denominator, that's a 1, then divide by the denominator squared. If you're doing it this way, I'd say that's excellent. Just it communicates to me you're getting the hang of this and you don't want to take those additional extra steps. But, doesn't hurt to do it in the notes. So let's be careful just a couple more times, just for the sake of really kind of reviewing it, just to convey once more how this should go. We'll take the derivative of the numerator, multiply by the denominator, subtract the numerator, multiply by the derivative of the denominator, divide by denominator squared. At this stage, this derivative here turns into a 1, so 1 times x plus 7, minus, there's a 1 over here, so minus x minus 5, times 1, over x plus 7 squared. So I'll still show this kind of setup, especially if the derivative gets worse on later sections. But if you're skipping to this step, I'd say it's always terrific. Next thing, we should simplify this as much as feasibly possible because we're solving the equation this time. So in the numerator, we have x plus 7 minus x plus 5 all over x plus 7 squared. So now new line, f prime of x is equal to, x is canceled, so just 12 over x plus 7 squared. So we've got a derivative down. Now, what does a critical number look like? It's a solution to f prime of x equals 0, or a critical number is also a value of f, let me say this better, a value in the domain of f for which the derivative does not exist. This is really easy to miss. It's super, super subtle. I don't think it's going to cause too big of a problem in our class, really, but if you're worried about these subtle little things, this is a pretty good one. the derivative does fail to exist right at -7. But -7 is not a critical number because -7 wasn't in domain in the very first place. So it's really weird. Sometimes when you run the quotient rule, you will pick up a critical number in domain of the original function. It just didn't happen this time. So if you're being hyper vigilant on that, good on you. We should always look out for it. But for the most of problems, it kind of goes like this. If we had something like this, -7 missing in domain, and that's the only value that's a problem of the derivative, we're still okay. It was not in the domain in the first place. Next interesting issue about this function is, how would we solve this equation? Let's pop it out a little bit to really focus on it. 12 x plus 7 squared equals 0. Solutions to equations like these only involve the numerator. That's a pretty bold statement. Why is that true? It's because you can immediately clear the denominator on this. You can make your very first step in solving this equation to go multiply by x plus 7 squared on the left, multiply by x plus 7 squared on the right, and you get a new equation, 12 equals 0. Or you might visualize it differently. You might visualize it by saying, this is just a cross product. Cross multiply denominator into 0, essentially annihilating it. All that matters is just your numerator now. But that equation isn't even true. That is false. And what that tells us is that this function, f of x, the original one, has no critical numbers. None whatsoever. That's kind of weird as a function altogether. Let's take another look at this one, just to see what would that look like. F of x equals, we expect a discontinuity right at -7, vertical asymptote. That's part of the picture of why things are going wrong, potentially. So x minus 5 divided by x plus 7. We have a vertical asymptote right at -7. Let's see what else the function does. It gets lower and lower going off to the left towards a horizontal asymptote at height 1. But that's not a minimum it's heading towards because it plummets in this direction. Same issue over here. It's getting higher and higher to its horizontal asymptote, but no maximum because it's blowing up in this direction. No maxes or mins whatsoever on that function, it turns out. It's just a bizarre function. That can happen. Just because we define critical numbers doesn't mean they always exist. It's kind of like the limit. We define an interesting object, and then we have to say, sometimes nothing happens when we go to take it, look at it. Limit fails to exist a lot, so does the derivative, and so does the concept of critical numbers in the first place. But this is the major rundown of what's going on in these notes. The next thing we're going to do is look at the so-called closed interval method twice on 2 different problems to really find and construct the absolute maximum, absolute minimums of our functions when there's no graph whatsoever. Any questions at all, folks, before we take a look at that last technique?
When you said domain is negative infinity and -7 union with -7 and infinity, what's the purpose of that in this problem?
That's a great question.
Well, 0 is false.
Sorry, say again?
If I did this, I would just say 12 equals 0 is false, and that would be the end answer, right?
Yeah, absolutely. The issue with what's written here in orange and the thing in red is in the definition of critical number itself coming from over here. Let's throw this in as part of part B. There's really 2 things we have to look for. When the derivative equals 0, that's what we were doing over here. We solved the derivative, set it to 0, got to 12 equals 0, and then we said no critical numbers. And if that's all you did on paper, you've done exactly what you need to do. But then the definition has that part. When the derivative fails to exist, you also get a critical number. This has actually caused problems in the past where people were paying really hyper attention to this one element right here. And when they got to the derivative, I've seen this on exam work in the past, people noticed, hang on, -7 is out of domain on the derivative. -7 is a value for which the derivative actually doesn't exist outright. Let's actually add that to the notes. F prime at -7 does not exist. So once you spot that, you might have said -7 is the critical number. However, let's take a look. A critical number of a function is a number C in domain of F. -7 was out of domain. So if we noticed that, we wouldn't have gotten tripped up on that piece of information here when we got to that derivative there. So it's kind of a weird problem, right? It's where if you're extremely vigilant on that small nuance, it actually could have caused trouble. That's a little bit awful in a sense, right? And what's in orange and purple is just a way to avoid that kind of trouble. This is not going to come up a lot in our class. It's just something we have to mention because it's a required part of the definition as well. But other questions or comments so far? Okay, well, let's take a look now at the so-called closed interval method. I put the extreme value theorem right here because really in spirit, that's what the closed interval method really is. But like we mentioned before, the extreme value theorem just says you have to have a continuous function f. Now, the closed interval method, it says to find the absolute maximum and minimum values of a continuous function f. So those hypotheses are matching up. Our continuous function f is on a closed interval. On the method, it says your continuous function f is also on a closed interval. So really, they're the same kind of theorem in a sense, except this is more of an algorithm or a method that takes a known theorem and shows you the process of actually getting the absolute maximums and minimums. Extreme value theorem didn't discuss it whatsoever. So think of the closed interval method as we're going back to extreme value theorem with the goal of producing absolute maximums, absolute minimums. So for example, that function there is continuous. This domain is closed. There is now a firm guarantee of an absolute maximum and minimum on the domain. Using this method, it's just a step-by-step process of finding those values. Well, let's give this a try, see what we can get. But any questions first, folks, on this one here? Okay, this one's kind of a nicer one because the algebra doesn't get too bad. But it's not fair to only do nice problems. When we come back on Thursday, still remembering my schedule. When we come back on Thursday, we'll do a really nasty one. This one is as bad as it could get in the homework and worse than it would be on a real exam. So this is kind of like a worst case situation. Product rules involved, non-standard equation solving techniques are involved as well. So we'll leave that when we come back on Thursday. Let's give this one a try. Step 1 says, find the critical numbers of your function. That was the first thing we were looking into. So here's how it goes. You first just simply differentiate your function. And it's a quick derivative. We get derivative 1 on that. Derivative of natural log x is 1 over x. So we're done with the derivative part. To actually get the critical numbers, the note in blue says, now set it equal to 0 and solve. So if we're doing f prime of x equaling 0, this becomes 1 minus 1 over x equals 0. And we want to solve this equation right here. I'd say the natural way to go is just add 1 over x to both sides. 1 is 1 over x. Then at this equation, multiply both sides by x. X would then equal 1. And we've done it. We found the solution. So x equals 1 is the crit. All right, crit for critical number, hash for number of f. So this was step 1. Now, for step 2, first let me say step 1, just to organize my work on here. Step 2, well, really step 2 and 3 kind of go together. Step 2 is a function evaluation step. Find the values of f at the endpoints of the interval when it refers to the endpoints of the interval, we're talking about those endpoints, 1/2 and 2, and at the critical numbers as well. So we do 3 function evaluations because we only had 1 critical number. But notice something kind of tricky about all this. We use the derivative, set it to 0 and solve to get the critical number. But step 2 is talking about f itself, the original function, that one. So we have multiple functions on the table. Labeling them as you use them is really smart for the sake of just organizing and separating things out in our mind so we don't conflate and confuse them together. So in step 2, we'll take a look at f at lower bound, 1/2. That's going to be equal to, using this function, 1/2 minus natural log 1/2. Then we take a look at f at either the other value 2, or let's go for the middle value 1, the critical number. F at 1 equals 1 minus natural log of 1. Natural log of 1 is 0, so we already have an exact value here. We get exactly 1. Then we go back to the last boundary value, evaluate f at 2, which means over here we're plugging in 2 minus natural log 2. Now, next thing I need is some estimates. I can't tell if 1/2 minus natural log 1/2 is bigger or smaller than 2 minus natural log 2. These have a way of being a lot trickier than we'd like. So we do need a calculator here. Let's take this and just get a fast estimate. 1/2 minus natural log 1/2 is about 1.19. Second calculator estimate is that 2 from down here minus natural log 2. That one is a 1.31. Again, I would have had no idea if 1 was above or below. That's really, really tricky, turns out. But once we find those, we're done with step 2. We're basically done with the problem. We're on to step 3 now. This goes fast because the function was nice. The next problem when we come back on Thursday takes a little bit more time to run through. Step 3 says, largest value in step 2 is your absolute maximum. Where is it? That would have been this. Notice what I'm highlighting though. We can't give the approximation value. Our answer is the exact value. That'll be the expectation on WebAssign. They complain about a lot. Even if you have a really good approximation, we need the exact value. And this will be the assumption on quizzes and exams as well. Let's start by saying absolute max is equal to 2 minus natural log 2. So it's not the approximation. It's not the input value, 2 itself. It's the output, the y-axis value. So largest value is the absolute maximum. Smallest value is the absolute minimum. That means it was this one. I'll highlight that part. If you gave me 1 minus natural log 1, that's correct too. This is just as correct, and it's also exact. So we'll say here, absolute min equals 1. This one, the one in green, not the critical number 1, not because you get anything wrong, but you don't want to think you're giving the input. Always think you're giving the output. That's just for safety's sake when they're different, like on this one here. So if we were to plot this function, we would see there should be an absolute maximum and an absolute minimum at those values. I'll leave that for your further investigation if you're curious, since we're really short on time. But any last questions, folks? I'm running through the whole method for this one. Okay, so that's the whole method. We're going to use this for optimization. And when we go into our next section on Wednesday, after finishing this work, it'll be about the first derivative test and the second derivative test. We're going to use those to find local minimums, local maximums. Because this one is just about absolute maximums and minimums. We have to give the local ones some love as well. But have a great afternoon, folks. When we come back on Thursday's class, that's what we'll be working towards. Yep, take care.